Let's jump right in. Think about it. A single oil and gas well can guzzle literally millions of gallons of water. So in an industry built entirely around extracting resources from the ground, how do we actually measure the true cost of the other most precious resource required to pull it off? I mean, water. When the rules are this complex, the environments are highly sensitive, and the stakes for both the business and the local community are just sky high. Counting every single drop isn't just a best practice anymore, right? It's an absolute fundamental requirement.
Welcome to The Explainer. Today, we're zeroing in strictly on the Sustainability Accounting Standards Board, or SASB framework, specifically for the oil and gas exploration and production sector. We're going to decode the complex mechanics behind their water management metrics together. Basically, we're figuring out exactly how these critical numbers are calculated under the hood.
Here is what we're covering today. First, the water management challenge. Then, assessing baseline water stress. Next, tracking recycled produced water. After that, monitoring fracking water quality. And finally, the value of these metrics. Let's get to it. Section 1, the Water Management Challenge. Look, depending on the extraction technique you're using, exploration and production operations can consume massive quantities of water. And, this exposes operators to some pretty severe environmental risks, like sudden supply shortages or local contamination issues. Plus, there are the serious financial risks, right? Think regulatory compliance costs and community disruptions. SASB addresses these risks head-on. In their water management section, they require very specific quantitative metrics to track all this. We are going to break down the exact calculations for 3 of the most complex ones on their list. But to calculate our very first diagnostic metric, we really have to start with a fundamental question. When an energy company withdraws water, what exactly counts as a high-stress region? It can't just be a subjective guess, right? We need a highly standardized definition. Section 2, assessing baseline water stress. Okay, this directly addresses SASB metric EM40A1.1, which tracks the percentage of water withdrawn and consumed in geographically sensitive areas. The standard actually mandates the use of a very specific tool here, the World Resources Institute's Aqueduct Water Risk Atlas. According to the WRI, a location is officially flagged for high baseline water stress if its score falls in the 40 to 80% range, and it hits extremely high stress the second it crosses that 80% threshold. So, how does this translate into an actual calculation for compliance teams? Well, it's essentially a simple 3-step recipe. Step 1, you map out all your operations using that WRI Aqueduct tool to pinpoint the stress levels of your withdrawal locations. Step 2, you sum up all the water withdrawn, measured in thousands of cubic meters from only those high or extremely high stress areas. Step 3, you simply divide that sum by your total global water withdrawal. To put that into perspective, imagine a reporting scenario where a company withdraws 100,000 cubic meters of water in total. If 20,000 of those come from regions the WRI flags as high stress, their reported metric is exactly 20%. Bam! It instantly shows investors exactly how exposed that company is to local water scarcity. Now, withdrawing the water is really only half the story. Once all that water goes down a well, we have to ask, how do we track the fluids that actually come back up? Because this is a huge factor in operational efficiency, and it forms our second diagnostic metric. Section 3, tracking recycled produced water. This brings us to SASB metric EMEP140A2, which is all about tracking the sheer volume of fluids generated during operations and figuring out exactly where they end up. First, we kind of need to cut through the jargon, because the standard strictly differentiates between 2 types of fluid. You've got produced water, which is the natural brine obtained straight from the hydrocarbon-bearing rock formations during extraction, and then you have flowback. That's the recovered hydraulic fracturing fluid that operators actually pump down into the well, which eventually returns to the surface. Once you calculate the combined volume of both those fluids, the standard requires companies to track their final fate into 3 very specific buckets. Bucket 1 was the water discharged, meaning sent directly out to the environment or maybe a third-party treatment plant. Bucket 2 was it injected deep underground for disposal. Or Bucket 3 was it recycled, meaning it got reused in other wells or drilling processes. To actually prove recycling efficiency, the math is refreshingly straightforward. Step 1, track the total volume, again in thousands of cubic meters, of all the combined produced water and flowback you've generated. Step 2, isolate the volume that was specifically routed into that recycled bucket. And step 3, divide your recycled volume by your total generated volume. Simple as that. A higher percentage here is a huge win. It directly proves a reduced freshwater footprint and way lower disposal costs.
Okay, which leads us to a highly, highly sensitive question. When you're operating in your underground aquifers and surface water, how do operators objectively prove that the surrounding water quality hasn't deteriorated? Without just taking their word for it.
Section 4. Monitoring fracking water quality. Let's unpack metric EMEP 140-4. This is designed to impartially track the percentage of hydraulically fractured sites where ground or surface water quality has degraded compared to its original baseline. The beauty of the standard is that it removes all the subjectivity by defining exactly what deterioration means chemically. It gets super specific. Basically, deterioration occurs if testing finds a brand new presence of thermogenic gas, or if there's an increase in methane concentration of more than 5.0 milligrams per liter between samplings. Or finally, if BTEX compounds, that's benzene, toluene, ethylbenzene, and xyrenes, or total petroleum hydrocarbons, are suddenly found in higher concentrations than the initial baseline. And obviously, this testing doesn't just happen on a whim whenever it's convenient. The standard points to strict, mandated timelines heavily influenced by bodies like the Wyoming or Colorado Oil and Gas Conservation Commissions. An initial baseline sample absolutely must be taken prior to any drilling. Then, the ongoing monitoring kicks in. You need to sample 12 to 18 months after completion, followed by yet another sample 60 to 78 months after that previous one. We are talking about a serious, multi-year commitment to data tracking here. So the final calculation formula turns all that complex chemistry into one clean, digestible metric. Step 1, identify all your hydraulic fracturing well sites. Step 2, look at your testing data and flag any sites showing those specific chemical increases against their baselines that we just talked about. Step 3, divide the number of those impacted sites by the total number of sites. That final percentage is exactly what gets reported out to the public and the investors.
Section 5. The value of these metrics. We've gone pretty deep into the math together today, but why does all this highly structured data actually matter so much to the industry? The absolute crucial takeaway here is that these are not just annoying compliance checkboxes. By rigorously tracking baseline water stress, recycling rates, and water quality deterioration, companies are handing over objective, hard data about their long-term operational viability. This data reveals how resilient a company is to sudden water shortages, how efficiently they're actually operating, and how well they manage risks that could otherwise totally derail local community relations.
Which leaves us with one final thought. In an industry literally focused on pulling hydrocarbons out of the earth, water is effectively the hidden currency that makes the whole shebang possible. As regulations inevitably tighten and environmental scrutiny continues to ramp up, can any operator, or any investor for that matter, truly afford not to count every single drop? Thank you for joining me for this explainer as we decoded these vital SASB metrics. Keep learning, and I'll catch you next time.